Look up. Imagine a million worlds, teeming with life, scattered across the cosmos. Now, confront a chilling truth: the universe itself is a prison. Not of bars, but of distance, of energy, of time. A prison that ensures, even if they exist, they will never reach us. Gaze at the night sky. Two stars appear side by side. Your eyes perceive closeness. Your mind accepts this flat, ceiling-like view. This perception is the first deception. Those two stars, seemingly intimate, could be separated by hundreds of light years. They appear close only because your vision flattens immense depth into a two-dimensional image. Our minds evolved to gauge distances across fields, not trillions of miles. This shortcut becomes catastrophic when calculating the distance to a star. The nearest star system, Alpha Centauri, sits approximately 4.24 light-years from our Sun. The number sounds small. But a light-year is the distance light travels in 1 year, moving at almost 670 million miles per hour. 1 light-year equals nearly 6 trillion miles. Multiply that by 4.24, and Alpha Centauri is roughly 25 trillion miles from Earth. To count 25 trillion, one number per second, without pause, would take nearly 800,000 years. Entire civilizations would rise and fall before you finished. That is the distance to the closest star. Human intuition shatters at a scale. The vast Pacific Ocean could be laid end to end over 2 billion times to bridge the gap to Alpha Centauri. You still wouldn't arrive. And Alpha Centauri is considered close. The Milky Way galaxy itself spans roughly 100,000 light-years. Light, the fastest phenomenon, takes 100,000 years to cross it. Not a ship, but light itself. When we imagine alien visitors, we picture them as neighbors, their journeys difficult but achievable. But stars are not cities. They are grains of sand scattered through a volume so immense that even neighboring stars are separated by trillions of miles of empty vacuum. Even if intelligent life were common, say, 400,000 civilizations in our galaxy, their average separation would still be hundreds, or even thousands, of light-years. The geometry dominates. The illusion of the night sky, making stars appear reachable, is profoundly misleading. Their apparent closeness is a trick of human perception. Every assumption about alien visitation stems from this trick, the idea that stars are manageable destinations, like islands across an ocean. The reality is harsher. Interstellar space is a vacuum so complete, containing roughly 1 atom per cubic centimeter, compared to 25 quintillion molecules in Earth's air. It is almost nothing. That nothingness stretches for light-years. To cross from one star to another is to traverse absence. There are no waypoints, no refueling stations. Only distance, measured in trillions of miles. And distance does not negotiate. If an alien civilization is 500 light-years away, their light takes 5 centuries to reach us. A spacecraft, at a fraction of light speed, would need thousands of years. 5,000 light-years means a 50,000-year journey. These are not abstract numbers, they are relentless consequences of cosmic geometry. The galaxy is not a neighborhood. It is an archipelago, each star an isolated island adrift in oceans of vacuum. No technology can make the galaxy smaller. It cannot move stars closer. It cannot rewrite the blueprint of the Milky Way. Distance is the first wall. Before propulsion, before energy, before engineering, we must confront this scale itself. Because once you truly grasp these distances, once the flat dome illusion shatters into three-dimensional reality, the conversation shifts. It becomes a question of whether any civilization, anywhere, can meaningfully cross gaps measured not in miles, but in trillions upon trillions of miles. And that, chillingly, is only the beginning. Distance by itself does not make something impossible. You can cross an ocean, given enough time. You can circle a planet, if you have the endurance. In principle, you could even drift between stars, if you were willing to wait tens of thousands of years. But there is a reason serious discussions about interstellar travel do not focus on drifting. They focus on speed. Because the only way to reduce a journey from geological time scales to something that fits within the lifespan of a civilization is velocity. And velocity at interstellar scales comes with an energy price so severe that it transforms distance from an inconvenience into an impenetrable wall. To understand this, begin with something modest. Imagine a robotic probe weighing 1,000 kilograms. Roughly the mass of a small car. No crew, no life support, just instruments, a power source, and a communication system. Now, a simple question: how much energy does it take to accelerate that probe to 10% of the speed of light? 10% of light speed is about 30,000 kilometers per second. At that velocity, you could travel from Earth to the Moon in under 13 seconds. It sounds fast, because it is. But even at 10% of light speed, the nearest star system, Alpha Centauri, is still more than 40 years away. The kinetic energy required to accelerate a 1,000 kilogram probe to that speed is approximately 4.5 times 10 to the 17th power joules. That number means little without context. Compare it to something familiar, a large nuclear power plant. Over an entire year, such a plant generates roughly 3 times 10 to the 16th power joules of energy. Accelerating our small probe to 10% of light speed would require more than a decade of that plant's total output, devoted entirely to one launch. And that is only acceleration. If you want the probe to slow down when it reaches its destination instead of streaking past the star in a matter of hours, you must supply the same amount of energy again, in reverse. The energy bill doubles. Now, increase the mass. Replace the small probe with a vessel capable of carrying even a minimal crew. Add radiation shielding, life support, structural reinforcement, navigation hardware, redundancy systems. The mass climbs from 1,000 kilograms to hundreds of thousands, or even millions. The energy requirement scales directly with mass. Multiply the mass by 1,000, and you multiply the energy by 1,000. This isn't a technological inefficiency. This is physics. Kinetic energy increases with the square of velocity. Double the speed, and the required energy quadruples. As you approach the speed of light, relativistic effects begin to dominate. The effective mass of the object increases. Each additional increment of speed demands disproportionately more energy than the last. At 90% of light speed, the energy required is not 9 times greater than at 30%. It is vastly more. At 99%, it becomes extreme. At 100%, it becomes infinite. That word is not rhetorical. According to special relativity, accelerating an object with mass to the speed of light would require infinite energy. Infinite energy cannot be generated. Chemical rockets are immediately eliminated. Their exhaust velocities are too low. The rocket equation ensures that fuel requirements increase exponentially with desired speed. To reach even a small fraction of light speed using chemical propulsion would require more propellant than exists on Earth. Nuclear fission improves the situation slightly. Nuclear fusion improves it further. But neither changes the fundamental relationship between mass, velocity, and energy. They only provide more energetic ways of paying the same, crushing bill. Even antimatter, the most energy-dense fuel theoretically possible, does not erase the cost. Matter-antimatter annihilation converts mass directly into energy, according to Einstein's E equals mc squared. It is the most efficient reaction allowed by physics. And it is still not enough to make interstellar travel trivial. To accelerate even a modest spacecraft to a significant fraction of light speed using antimatter would require quantities far beyond anything humanity has ever produced. The total amount of antimatter ever created in laboratories amounts to less than a grain of dust. Producing even a single gram would consume extraordinary resources. Scale that to the hundreds or thousands of kilograms required for a meaningful interstellar mission, and the numbers become so extreme they exit practical discussion. Some propose external propulsion methods to bypass the need for onboard fuel. Laser-driven light sails are one example, a powerful laser array beams energy onto a reflective sail, pushing the spacecraft forward without carrying its own propellant. In theory, this removes the exponential penalty of the rocket equation. In practice, it introduces a different barrier. To accelerate even a small probe to a fraction of light speed would require laser arrays producing power comparable to the electrical output of entire nations. And such a system can only push. It cannot decelerate the craft at its destination unless another equally massive laser array has already been constructed there, which assumes someone has already made the journey. Every propulsion concept, when examined closely, converges on the same conclusion: interstellar travel demands energy expenditures that are not merely large, but civilizational in scale. And energy is not just about availability, it is about allocation. Even a highly advanced civilization, capable of harnessing the full output of its star, what physicists call a Type II civilization on the Kardashev scale, must decide how to distribute that power. Powering cities, sustaining ecosystems, running computational systems, maintaining infrastructure. Diverting a significant fraction of stellar output to accelerate a single vessel for decades is not trivial. Even at that scale, it represents a commitment comparable to redirecting planetary resources toward a single project with no guarantee of success. And that is only for one mission. To explore systematically, to visit dozens or hundreds of star systems, would multiply that energy demand again and again. More importantly, greater energy does not alter the speed limit. It does not remove relativistic constraints. It does not make the galaxy smaller. It simply allows you to pay the same non-negotiable price more comfortably. The laws governing motion do not relax for intelligence. An alien civilization millions of years more advanced than ours still faces the same equations. They can improve efficiency. They can reduce waste. But they cannot reduce the minimum energy required to move a given mass at a given velocity. That minimum is fixed. It is determined by the mass of the spacecraft and the speed of light. No engineering breakthrough changes that relationship. No innovation lowers it below the floor set by physics. This is the second wall. Distance defines how far they must travel. Energy defines whether they can travel fast enough for it to matter. And when you combine the two, when you calculate the energy required to cross hundreds or thousands of light-years within the lifetime of a civilization, you encounter numbers that do not merely challenge engineering. They challenge feasibility itself. Because interstellar travel is not just a journey. It is an energy transaction on a scale that strains even the imagination of advanced civilizations. And the universe does not offer discounts. Imagine the engineering challenges have been solved. The immense resources have been gathered. The ship, a marvel, has been constructed and pushed to a meaningful fraction of the speed of light. The home star shrinks behind it. The destination star remains a distant point ahead. Now, the limiting factor is no longer distance, nor the energy to conquer it. It is duration. At 10% of light speed, the nearest star system, Alpha Centauri, is still more than 4 decades away. That is the closest possible target. A civilization slightly farther out, 100 light-years distant, would require a journey of 1,000 years. At 500 light-years, the travel time stretches to 5,000 years. At 1,000 light-years, 10,000 years pass before arrival. 10,000 years ago on Earth, writing had not yet emerged. The oldest surviving monuments today are younger than that. Entire languages have appeared and vanished within far shorter spans. No civilization we know has remained culturally or politically stable across such intervals. Institutions fracture. Governments collapse. Scientific knowledge is lost and rediscovered. An interstellar voyage lasting millennia must survive more time than the society that launched it has likely ever experienced. One proposed answer is the generation ship, a vast, self-contained habitat carrying a population large enough to reproduce and maintain genetic diversity across centuries. The original crew would not arrive, their descendants would. But sustaining a closed ecosystem for thousands of years is not an incremental extension of existing spaceflight. It is an entirely different category of problem. Every molecule of oxygen must be recycled. Every drop of water must be purified and reused indefinitely. Agricultural systems must function continuously without seasonal resets, without soil renewal from planetary cycles, without external input. Even on Earth, with gravity, sunlight, and the stabilizing influence of a planetary biosphere, fully closed ecological systems have struggled to remain balanced for more than short experimental periods. Small chemical imbalances accumulate. Microbial populations shift. Extend that system across centuries in hard vacuum, exposed to radiation without external correction, and the probability of failure rises steadily. Mechanical systems add another layer of fragility. Metals fatigue, seals degrade, electronics suffer radiation damage at the atomic scale. Even highly reliable components eventually fail under constant stress. Reliability mathematics is unforgiving. A system with a 99.9% chance of surviving each year still faces overwhelming odds of failure across 10,000 consecutive years. Multiply that risk across thousands of interdependent systems, and the probability of uninterrupted operation approaches zero. Redundancy reduces risk, but redundancy increases mass. Increased mass increases propulsion demands. Propulsion demands increase system complexity. Complexity introduces new failure points. The challenges compound rather than cancel. Beyond biology and mechanics lies sociology. A society confined to a vessel for generations would evolve in isolation. Cultural drift would be unavoidable. The mission's purpose would shift as memories of the originating world fade into distant history. Children born aboard the ship would not experience the departure as a sacrifice. For them, the vessel would be normality. The destination star would not be a homecoming. It would be an abstract directive inherited from people long dead. Political structures would change. Leadership would pass through crises and reforms. Conflicts would arise over resources, ideology, and authority. Human history demonstrates that even under stable planetary conditions, societies rarely remain cohesive for extended periods. A generation ship amplifies those pressures. There are no external trade partners, no immigration, no expansion. Population levels must be carefully controlled. A famine caused by agricultural malfunction is not local, it is global within the vessel. Over centuries, the psychological strain of confinement alone becomes significant. Time also erodes connection with the origin civilization. A mission traveling 1,000 light-years at 10% of light speed requires 10,000 years to arrive. During that interval, the launching civilization continues to change. Technologies advance. Cultural values shift. Entire species may alter their biology through evolution or engineering. The society that launched the mission may collapse, merge into something new, or disappear entirely. By the time the travelers arrive, they represent a version of their civilization that no longer exists. Communication does not bridge this gap. Signals travel at light speed. A message sent across 1,000 light-years takes a millennium to arrive. A reply requires another millennium. Each exchange spans 2,000 years. At that scale, dialogue is functionally impossible. Engineering updates, political directives, even simple reassurance arrive centuries too late. The vessel becomes autonomous from the moment communication lag exceeds practical relevance. Relativistic time dilation offers partial relief to the travelers. At velocities approaching light speed, time passes more slowly on board relative to stationary observers. A crew traveling at 90% of light speed experiences time at less than half the rate of those at rest. But meaningful time dilation requires extreme velocities, and extreme velocities demand extreme energy. The closer one approaches light speed, the steeper the energy curve becomes. Time dilation reduces subjective travel duration while increasing the energy barrier dramatically. It does not eliminate the millennia experienced by the origin civilization. Another complication emerges from technological progress itself. If propulsion improves over time, any mission launched today risks being overtaken by a faster mission launched centuries later. Rational planning suggests waiting for better technology. But indefinite waiting means no mission is ever launched. This creates a paradox: launch now and risk obsolescence, or delay and postpone indefinitely. Even self-replicating probes, machines designed to reproduce using local materials in other star systems, remain constrained by time. A wave of such probes spreading at 10% of light speed would require roughly 1 million years to cross the galaxy. 1 million years exceeds the lifespan of nearly every complex species known. Civilizations rise and fall in far shorter intervals. The probes might complete their mission long after their creators are extinct. Throughout this entire process, entropy continues. The second law of thermodynamics ensures that order degrades into disorder over time. No structure maintains perfect stability indefinitely. Biological systems accumulate mutations. Mechanical systems accumulate wear. Information storage degrades unless constantly refreshed. Interstellar travel is not merely a question of reaching a destination. It is a commitment to maintaining order against entropy for durations that dwarf recorded history. Distance sets the scale. Energy sets the cost. Time determines whether the effort can remain coherent long enough to matter. A civilization capable of crossing interstellar space must not only master propulsion. It must sustain purpose across centuries, maintain mechanical integrity across millennia, and survive cultural transformation without losing the reason it began the journey. The longer the trip, the more fragile that continuity becomes. Time does not obstruct interstellar travel in a dramatic way. It does not explode ships or block engines. It simply stretches the journey until civilizations, machines, and intentions unravel under its weight. Even if a civilization overcomes distance, pays the energy cost, and commits to surviving the passage of time, one problem remains before the journey even begins. They have to know where to go. From an interstellar distance, Earth is not a blue marble hanging clearly in space. It is not visibly alive. It is not broadcasting a beacon that says, "Inhabited." It is a small rocky planet orbiting an ordinary star. The Sun is one of roughly 400 billion stars in the Milky Way. It is not exceptionally large. It is not exceptionally bright. From hundreds or thousands of light-years away, it blends into a dense field of similar stars. There is nothing about it that demands attention. To detect Earth directly from even a few light-years away requires extremely sensitive instruments. The planet is roughly 8,000 miles in diameter. Compared to the Sun, it is a tiny speck reflecting a small fraction of the star's light. Resolving a planet that small at distances of hundreds of light-years would require telescopes with apertures measured in hundreds of kilometers. And even then, what would they see? They would see Earth as it was when the light left it. If a civilization sits 1,000 light-years away, the light reaching their instruments tonight departed Earth 1,000 years ago. They would see the planet as it existed in the medieval period. No radio signals, no satellites, no industrial pollution, no visible city lights detectable at that range. They would see a rocky planet with an oxygen-rich atmosphere. Oxygen suggests biological activity. It does not guarantee intelligent life. Many worlds could display atmospheric chemistry produced by microbial ecosystems. To commit thousands of years and enormous energy resources to visit a planet based solely on atmospheric oxygen would require extraordinary confidence that something unique awaits. Earth is not unique in a way that is obvious from a distance. Our radio signals have been leaking into space for roughly a century. That means they have traveled about 100 light-years in every direction, forming a sphere of detectability 200 light-years across. That sounds large. It is not. The Milky Way spans roughly 100,000 light-years. Our radio bubble covers a minute fraction of its volume. A civilization 1,000 light-years away has not yet received any sign of our technological existence. Even when those signals arrive, they will be faint. Electromagnetic radiation obeys the inverse square law. As a signal spreads outward, its strength decreases with the square of the distance. Double the distance, and the signal becomes 4 times weaker. Increase it tenfold, and it becomes 100 times weaker. By the time a broadcast from Earth travels hundreds of light-years, its energy is diluted across an enormous sphere. Distinguishing it from background cosmic noise becomes extraordinarily difficult. Natural radio emissions from stars, pulsars, and other astrophysical processes fill the galaxy. Our signals must compete with that background. Detection is not guaranteed. Now consider the scale again. If intelligent civilizations are rare, perhaps 1 in every 10 million stars, then the nearest one may be thousands of light-years away. Their instruments would need to detect a faint oxygen signature from Earth's atmosphere across that gulf before our radio signals even reach them. If intelligent civilizations are more common, separated by only a few hundred light-years, the detection problem remains. Hundreds of light-years is still a distance at which Earth appears as a dim pixel next to an ordinary star. From their perspective, the galaxy contains millions of potentially habitable planets. Many of those worlds may exhibit interesting atmospheric signatures. Why choose ours? Interstellar travel, as established earlier, is a project measured in millennia and staggering energy costs. No civilization would initiate such a mission casually. The target must justify the expenditure. But Earth does not advertise itself. Even advanced astronomical techniques, such as the transit method, detecting the slight dimming of a star as a planet passes in front of it, depend on geometric alignment. Only observers located along the plane of Earth's orbit would see our planet transit the Sun. For most positions in the galaxy, that alignment does not occur. If their line of sight does not intersect our orbital plane, Earth never blocks the Sun from their view. In that case, the planet remains hidden. Some might argue that a sufficiently advanced civilization could map every star system in detail. Perhaps they deploy vast telescope arrays or interferometers capable of resolving distant planetary surfaces. Even then, resolution decreases with distance. To resolve features on Earth from 1,000 light-years away would require an aperture thousands of kilometers across. Constructing such an instrument represents a megastructure-scale engineering project. And what would they gain? A faint image of a small world orbiting a typical star. There is no obvious signature that screams advanced civilization across those distances. Industrial pollutants in our atmosphere are trace components compared to oxygen and nitrogen. Night-side illumination from cities is extremely faint relative to reflected starlight. From interstellar range, Earth does not glow with intelligence. Now reverse the perspective. We have discovered thousands of exoplanets in recent decades. Many reside in the habitable zones of their stars. Some show atmospheric signatures consistent with water vapor or possible biosignatures. We do not launch starships toward them. Even if we confirm microbial life on a planet 50 light-years away, the cost of physically traveling there remains prohibitive. A civilization evaluating Earth would face the same calculation. Distance is enormous. Energy is staggering. Time is measured in centuries or millennia. And the target is uncertain. Committing a mission under those conditions requires a compelling reason. Curiosity alone may not justify a multi-thousand-year investment. There's also the problem of motion. Stars are not stationary. They orbit the galactic center at hundreds of kilometers per second. Over thousands of years, their positions shift. A star system targeted today will not occupy the same coordinates centuries later. Accurate long-term trajectory planning must account for stellar motion, gravitational perturbations, and cumulative navigational error. A slight miscalculation at departure can result in missing the target system by billions of miles after thousands of years of travel. Navigation across interstellar distances demands extraordinary precision. There are no landmarks between stars, no gravitational anchors beyond distant suns. Course corrections require additional energy. Additional energy requires additional fuel. And the closer the spacecraft approaches relativistic speeds, the more destructive even tiny particles become. A single grain of dust impacting at a fraction of light speed can release explosive levels of kinetic energy. Shielding adds mass. Mass increases energy demand. All of this effort would be directed toward a planet that may or may not host intelligent life by the time the ship arrives. Because life evolves. A civilization detected 1,000 light-years away would appear as it was 1,000 years ago. The travelers would arrive 10,000 years later if traveling at 10% of light speed. By then, the original civilization may have transformed beyond recognition or disappeared. The target is not static. The galaxy is dynamic. Stars move. Planets evolve. Civilizations rise and fall. An alien species deciding whether to journey toward Earth must evaluate incomplete information about a distant world, accept extreme energy expenditure, endure millennia of travel, and arrive in a future they cannot predict. All without certainty that the objective justifies the cost. Interstellar travel is not like exploring a nearby island with visible shores. It is like launching across an ocean toward a signal that may not even be there anymore. And this is the fourth wall. Before crossing the void, before accelerating to relativistic speed, before sustaining a civilization across centuries, they must first know that Earth is worth visiting. From most of the galaxy, we're not visible. From even fewer vantage points, we are detectable. From almost nowhere, we're compelling enough to justify a journey measured in thousands of years. The universe does not only separate civilizations with distance and energy. It hides them from one another. At this point, a common response emerges. The distances are vast. The energy requirements are extreme. The time scales are overwhelming. But perhaps we are thinking too narrowly. Perhaps an advanced civilization would not attempt to crawl between stars at a fraction of the speed of light. Perhaps they would bypass the problem entirely. Warp drives, wormholes, faster-than-light travel. These concepts are familiar from science fiction, but they also have roots in theoretical physics. The question is whether they represent real solutions or mathematical curiosities that collapse under physical scrutiny. Start with the speed of light itself. According to special relativity, the speed of light in a vacuum is not simply a fast velocity. It is a structural feature of space and time. It represents the maximum speed at which information or matter can travel. As an object with mass accelerates toward light speed, its relativistic mass increases. Each additional increment of speed requires more energy than the previous one. The energy requirement does not rise linearly. It rises asymptotically. At exactly light speed, the required energy becomes infinite. Infinite energy is not a large engineering challenge. It is a physical impossibility. No amount of technological progress allows a civilization to generate infinite energy. This limit has been tested repeatedly. Particle accelerators push subatomic particles to velocities extremely close to light speed. As they approach that limit, the energy required to accelerate them further increases dramatically, exactly as relativity predicts. The equations do not bend. The speed of light is not a barrier imposed by current technology. It is embedded in the geometry of spacetime. To travel faster than light, one would need to circumvent this geometry. One proposed method is the Alcubierre warp drive, developed by physicist Miguel Alcubierre in 1994. The idea does not involve moving a spacecraft through space faster than light. Instead, it proposes compressing space in front of the craft and expanding it behind, creating a warp bubble that carries the vessel forward. In principle, the ship inside the bubble never exceeds light speed locally. Space itself is the moving. The mathematics are valid solutions within general relativity. But the physical requirements are severe. A warp drive demands exotic matter with negative energy density. Material that exerts gravitational repulsion rather than attraction. No such substance has ever been observed in usable quantities. Negative energy appears in small, transient quantum effects, but nothing remotely close to the stable, large-scale forms required to sustain a warp bubble. Early calculations suggested that creating a warp field would require energy equivalent to the mass energy of the entire observable universe. Later refinements reduced the estimate dramatically, but only to levels comparable to the mass energy of a planet like Jupiter converted entirely into energy. That is not an engineering gap. That is an absence of physical feasibility. Wormholes, or Einstein-Rosen bridges, offer another theoretical shortcut. In theory, a wormhole connects two distant points in spacetime through a tunnel-like structure. Travel through such a structure could be nearly instantaneous regardless of the external distance. But stable, traversable wormholes face the same obstacle as warp drives. They require exotic matter to remain open. Without negative energy density to counteract gravitational collapse, the wormhole would pinch shut faster than anything could pass through it. Additionally, wormholes introduce problems with causality. Faster-than-light travel combined with relativity can produce time paradoxes, allowing effects to precede causes in certain reference frames. Many physicists suspect that fundamental laws, sometimes referred to as chronology protection, prevent such paradoxes from occurring. In other words, the universe may forbid stable wormholes precisely because they would violate consistent cause and effect relationships. There is no experimental evidence that traversable wormholes exist. No astronomical observation has revealed a natural one. No laboratory experiment has hinted at controllable negative energy in the required form. Another idea involves quantum entanglement. Entangled particles exhibit correlations across distance that appear instantaneous. Some speculate this could enable faster-than-light communication. But entanglement does not transmit usable information faster than light. The statistical outcomes observed still require classical communication to compare results. Relativity remains intact. Each proposed loophole ultimately encounters the same constraint. Either it requires forms of matter never observed in nature, or it violates causality, or it demands energy scales beyond any realistic interpretation of physics. The appeal of faster-than-light travel lies in imagination. The constraints arise from experiment. Relativity is not a fragile theory awaiting collapse. It has survived more than a century of increasingly precise tests. Time dilation has been measured with atomic clocks. Gravitational waves have been detected. GPS satellites must account for relativistic corrections to function properly. The speed of light limit is woven into every verified prediction of modern physics. Overturning it would require rewriting not just one equation, but the entire framework of spacetime. Could future discoveries expand our understanding? Possibly. Science is always open to revision, but speculation about unknown physics cannot serve as a practical bridge across light years. An advanced civilization does not gain exemption from physical law simply by being advanced. A species millions of years older than humanity still exists inside the same spacetime geometry. It still obeys conservation of energy. It still experiences entropy. Greater knowledge might allow more efficient propulsion. It cannot erase relativistic constraints. Even a civilization harnessing the full energy output of its star, a so-called Type II civilization, would still face the same limit. More energy allows more attempts. It does not allow infinite acceleration. A Type III civilization harnessing the energy of an entire galaxy would still be bound by the same light speed ceiling. Power does not modify geometry. If faster-than-light travel were physically possible in a stable, controllable form, the universe itself would look different. We would expect to see evidence of rapid galactic colonization, signals, structures, or anomalies inconsistent with slow expansion. Instead, the cosmos appears quiet. The absence of obvious galaxy-spanning activity suggests either that civilizations are rare, or that faster-than-light travel is not available to them. Physics does not promise convenience. It promises consistency. The consistency of relativity, confirmed across scales from laboratory experiments to astrophysical observations, indicates that interstellar travel must remain sublight. Sublight travel reintroduces every barrier already discussed. Distance becomes enormous. Energy becomes staggering. Time becomes dominant. Without faster-than-light shortcuts, the galaxy does not shrink. Each star remains isolated by light-years of vacuum. Each civilization remains constrained by the same cosmic architecture. The dream of effortless interstellar travel depends on rewriting the laws that define space and time. Those laws have not shown signs of yielding. The speed of light is not a technological obstacle waiting for innovation. It is a property of the universe itself. And as long as it remains, every civilization, no matter how intelligent, must navigate within its boundaries. If distance stretches beyond intuition, if energy demands exceed practicality, and if time erodes every mission long before arrival, then a larger conclusion begins to form. The question shifts. It is no longer, are they out there? It becomes, even if they are, could any two civilizations ever meaningfully meet? The Milky Way is roughly 13 billion years old. Over that span, stars have formed, lived, and died in cycles. Planets have cooled. Chemical complexity has unfolded. On at least one world, Earth, intelligence emerged. There is no obvious reason to believe Earth is the only place where this occurred. Given the number of stars and the prevalence of planets, it is plausible that life has arisen many times. It is plausible that intelligence has emerged repeatedly. Entire civilizations may have existed millions of years before humanity evolved. Others may arise long after we are gone. But the galaxy is not just large in space. It is vast in time. Civilizations are not permanent. Human technological society has existed for only a few centuries. Even if it endures for thousands of years more, that span is microscopic compared to galactic history. A civilization may flourish for 10,000 years, an extraordinary achievement, and then decline, fragment, or transform into something unrecognizable. Now consider two civilizations separated by 1,000 light-years. Even if both achieve interstellar capability, their windows of opportunity must overlap. They must exist at the same time, they must both possess the desire and resources to attempt contact. The galaxy contains hundreds of billions of stars spread across 100,000 light-years. If civilizations are rare, separated by thousands of light-years, the probability that two such societies rise simultaneously and attempt to reach one another becomes small. If civilizations are more common, separated by only 100 light-years, the communication delay still stretches into centuries. The travel time stretches into millennia. Civilizations may rise and fall without ever knowing their neighbors existed. This idea reframes the silence of the cosmos. The absence of visitors does not require that intelligent life be rare. It may simply reflect that the structure of the universe enforces isolation. Each star system is like an island in a vast ocean. On Earth, islands separated by oceans can eventually connect through ships and aircraft because the oceans are finite and crossable within human lifetimes. The interstellar ocean is different. It is measured in light-years. It demands energy on planetary scales. It imposes travel times longer than civilizations endure. Even if a civilization develops self-replicating probes, machines that build copies of themselves and spread outward, the expansion front moves slowly compared to galactic dimensions. At 10% of light speed, crossing the Milky Way requires roughly 1 million years. 1 million years is long enough for continents to shift and climates to change. It is long enough for species to evolve or vanish. The civilization that launched the first probe would not recognize the galaxy when the last probe arrived at the opposite edge. Time decouples cause and effect across interstellar space. There is also the issue of motivation. Exploration requires purpose. A civilization must decide that the cost in energy, time, and risk is justified. That calculation depends on values, priorities, and internal stability. Not every society pursues maximal expansion. Some may focus inward. Some may transition into digital or virtual forms, reducing the incentive to colonize physical worlds. Some may conclude that the risks outweigh the benefits. Interstellar expansion is not an automatic consequence of intelligence. It is a choice, and that choice must persist across centuries of political and cultural change. The laws of thermodynamics add another constraint. Entropy ensures that maintaining order requires continuous energy input. Civilizations must invest resources simply to preserve themselves. Infrastructure, climate control, ecological balance, all demand energy. Diverting enormous power toward interstellar ventures competes with domestic stability. Over time, internal pressures may outweigh distant ambitions. The more advanced a civilization becomes, the more complex its systems. Complexity increases vulnerability. A single cascading failure, ecological, technological, or social, can destabilize the entire structure. If the lifespan of advanced technological societies is limited by self-inflicted risks or natural hazards, their interstellar window may be brief. Combine short civilizational lifespans with vast spatial separation, and the galaxy becomes a collection of isolated episodes rather than a connected network. There is a tendency to imagine a mature galaxy filled with star-spanning empires, continuous communication, and coordinated expansion. But that image assumes that physics allows rapid, sustainable movement between stars. If it does not, the default state is fragmentation. Each civilization illuminates its own system for a time, then fades. The light from that civilization, in the form of radio signals or atmospheric changes, spreads outward at the speed of light. But by the time it reaches distant stars, the source may already be gone. The receiving civilization, if it exists, must then decide whether to respond, knowing that any reply will take centuries to arrive and that the origin society may no longer be there. Communication becomes asynchronous on time scales that exceed cultural continuity. Under these conditions, even a galaxy filled with life can appear silent. Silence does not imply emptiness. It implies separation. The barriers described in previous sections, distance, energy, time, detection limits, relativistic constraints, do not merely make interstellar travel difficult. They shape the large-scale structure of civilization in the cosmos. They prevent rapid mixing. They prevent synchronized development. They prevent the formation of tightly connected interstellar communities. Instead, the most likely configuration is scattered intelligence, countless independent experiments in awareness, each unfolding within the gravitational well of its own star. From the perspective of any one of those civilizations, the sky remains quiet. They may search, they may listen, they may broadcast, but the signals are faint, the distance is immense, and the response times measured in centuries. The universe does not forbid life. It does not forbid intelligence. It does not even forbid interstellar attempts. What it appears to forbid is easy connection. Every star is separated by light years. Every light year represents nearly 6 trillion miles. Every attempt to cross that gap demands energy proportional to the mass of the ship and the square of its velocity. Every mission unfolds over durations longer than stable civilizations typically endure. These are not temporary technological challenges. They are consequences of how spacetime is structured. The result is a cosmos that may be populated but compartmentalized. A galaxy of isolated worlds. Each one potentially alive, each one potentially curious, yet divided from the others by barriers that do not yield to intelligence alone. If alien civilizations exist, they may be staring at their own night skies, performing the same calculations, reaching the same conclusion. The stars are visible, the distances are real, and reality itself may ensure that most civilizations never meet. The true count of isolated worlds, silently pondering the cosmos, could be an unnerving 1, 0, 0, 0, 0, 0, 0.